Hello, this is it. This is part 5 of the magnetism overview. Now I want to emphasize that once you've watched this and you've understood everything and you can apply it all, you're not done with magnetism, much less electromagnetism, because it's still the whole topic of induction and how changing magnetic fields create electric fields and create currents. But we'll come to that. So here are just some further applications of the reasoning and mostly of magnetic forces that we've seen before. Right? And there's some really fun effects here. So I'm just going to go through them fairly quickly. Hopefully this video won't get too long, but if you understand each one of these effects, then I think it will show that you've got a good grasp of the material. So the first one is called the Hall effect. That's by Edwin Hall. And what we do here is we imagine we've got a magnetic field. So those are the crosses, right? I guess I should have labeled this as my B field, right? It points into the page in this case. And then I've got some kind of object, and I'm going to pretend this is a conductor. That's crucial, right? So remember, a conductor means that the charges inside it can move around. So the conductor is neutral, but it has positive and negative charges in it. Now, the whole thing moves to the right. You gave it a push, you gave it a shove, it's moving through the magnetic field. So if you're a little positive charge sitting in here, right, your positive charge is moving to the right in a magnetic field that's pointing down, and with some hand gymnastics, velocity, field down, middle finger is going to pointing this way, right, this way here, I'm giving it a finger right there. How rude. You can experience a force up. Negative charges in the conductor, well, same right-hand rule, right? But because it's negative, the direction is flipped, you experience a force down. So what's the effect? Positive charges are going to gather up here, right? So we're going to end up with a bunch of pluses sort of hanging out up here. Of course, we really know it's negative charges that move away from there, because negative ones are the light electrons, positive ones are sort of stuck in place, but the effect is the same. And I'm going to get negative charges down here. So what does that do? That will create, let me just draw this thing again. Right, this is my piece of metal, and a bunch of plus charges up here, a bunch of minus charges down here. Right, just because this conductor as a whole is moving through the magnetic field, so I'm going to get an electric field because there's positive charges here, negative ones here. Electric field is going to be approximately down like this, right? So the separation of the charges due to the magnetic field and the motion through it creates an electric field, which means that now if you're a plus that's still, say, left in here, you're going to have a force down, electric force down, and a magnetic force up. If the magnetic force is still stronger, then you are also going to migrate up to your friends up here. Actually, they're not your friends because they're other plus charges and you don't like them, right? You get repelled by them. But the magnetic force is so strong, it's still going to move up. But the more pluses move up, the more minuses move down, the stronger the electric field gets until the two equal out, right? Until you get the difference between here and here, the electric field that's created is equal. So that if you are a little charge Q sitting here, QE is equal to the magnetic force, and the magnetic force is, of course, QVB. Right, by the Lorentz force law. Notice that the electric field is created by the magnetic field in a sense. Right? The magnetic field rearranges the charges, that creates an electric field, and that keeps happening. The electric field gets stronger until it is so strong that any charges still sitting in the middle now are balanced out in their force. If you're a minus sign, right, then your magnetic force would be down, but the electrostatic force would be up. Now, if you then remember that if the electric field is about constant in here, you can actually rewrite this as Q times delta V over delta x, where delta x is in this case measured vertically, that's equal to QVB. Notice that this is meant to be a big V, the potential, right, with this one is the velocity. So if you then get a voltmeter, right, what color am I going to use for voltmeter? I don't know, I've used them all. Here's my voltmeter. I'm going to hook this up. I'm going to get a reading. I'm going to get a reading that actually doesn't depend on Q at all, those will cancel out. That's the delta V that I get is delta X times Q times B. Sorry, not Q. Q's cancelled out. Cancel it. I'm going to get that the potential difference between the top and the bottom is delta X, the length of the thing, times the velocity, the speed it has, times the magnetic field strength. There would be a way to measure the magnetic field strength, because you can see how fast your conductor is moving, and you know how big your conductor is from top to bottom, right? But if you don't know what the magnetic field strength is, that would be a way to actually measure it with a voltmeter. Alright, that's first example. Second example, railguns. Now, railguns are cool. If you look them up on YouTube or something, you're going to find like videos of constructions the size of a house, and you put them on a warship or something, and you find these ginormous projectiles with enormous speeds. Like they're crazy big things. In the lab, we could actually build one that's much smaller and more sort of less scary. But let's figure out how they actually work. Right? They are a real thing. That's very expensive, I think, to maintain. And part of it is the reason I want to explain to you. But here's what you do. You hook up a battery. It has to be a really strong battery. And specifically, you're going to need a very big current. And you hook it up to two rails. Now, those rails here, is why it's called a railgun. And they're conducting. And across those rails, I'm going to put some kind of conductor. This is going to be our projectile. Now I drew it like a big stick just to make the connection, but like a rod. But it could have some other shape as long as it connects two ends. It's a conducting projectile. That's the thing we're going to shoot. So here's what's going on. The current, right, is going to run through here, and it's going to run through here. My current I. And that's going to create a magnetic field. By the curly hand rule, right, I can figure out that the current running through here creates a magnetic field that points into the page over here, out of the page over here. The current then runs through here. Of course, that also creates a magnetic field. I'm not going to write it down right now because we're going to worry about the effect of the magnetic field on this piece of the circuit. And then the current runs this way. So I'm going to get again, curly hand rule, right? Inside, I'm going to get the same current, of course, right? It's going to still point down. And outside, it's going to come out of the page. Hope you can visualize the magnetic field. So now this rail here is sitting in a magnetic field. Now it also has a current go through it, I. Right, same current, it runs all the way through. Now this current here is sitting in this magnetic field created by those other parts of the circuit. Now let's apply the right hand rule, therefore to figure out the force. The current is down, the field is, so the current is, let me turn this so I can not break my wrist again. Current, the red current in our projectile is this way. The field points down, so the force on this thing is this way. Right? It's going to be a force in that direction. Due to the magnetic field created by this. Now the calculation here isn't very easy, because of course the magnetic field created by this one gets weaker as we get away from it, but as we get closer to this one, the green one gets stronger. So to actually figure out the total force on this, like we'd have to do an integration, because the magnetic field is not constant, so we have to like add up each little tiny bit of this projectile, see what is the force on it. We can do it. Actually, I mean, it's not impossible. It's just a little bit lengthy, but you can totally do it as an exercise. Like, you have the knowledge and the tools to do this. Figure out what's the total force on this. Now, to make this actually work effectively, you need a very, very large current. You notice there's nothing of notable resistance in this circuit, right? It's just a really high voltage. With a high EMF. And we're going to get a gigantic current. Now then, this thing will start moving because it's just sitting on the rail. It's not like clamped in place. It'll start moving this way, but the circuit will still continue to be closed until it hits the end of the rails. And by that point, it has gained significant speed because it had a continuous force acting on it. And by doing this, you can actually make this thing accelerate like enormously into crazy speeds if you have an construction that's sizable enough. Put it this way, and a high voltage power supply that can also provide a very, very large current. I'm not entirely sure how you do this in like a realistic railgun. I know like the military sort of experiments with those on warships. Say, well, it's the only place you can really mount them, or buildings, right? Maybe you can have some kind of setup where you have a bunch of like giant capacitors to get a huge potential difference. You can charge them up gradually and then let them go. There's probably more than one way of doing it. But the point is, you get a giant current, you get a force on this, the thing accelerates to the right. It shoots off, and that is your railgun, right? It's on rails, and the projectile itself is part of that circuit. Now they don't last very long because those gigantic currents means you get a gigantic power output, and those rails, the projectile we shoot, we don't care what happens to it, right? It's gone. But the rails will get extremely hot within a fraction of a second, and they will wear out as a result very quickly. So the maintenance of one of those, at least a large one, is very significant. It's another application of creating magnetic fields and the forces on wires, right? In this case, one single circuit is both responsible for the creating the magnetic field and being the wire that's being moved. Of course, you could do the same exercise for the calculate forces on those rails, and you'll find that they get pushed outwards, right? You could do the same calculation. The magnetic field created by this part here is going to push the rail out, but we're going to assume the rail is fixed in place in a very sturdy way. By the way, one interesting little thing, you put a little circuit, and maybe I'm going to put a little resistor in, doesn't matter. There's a current flowing around it. You can check that if each part of the wire creates a bit of a magnetic field that acts on the other wires, overall the circuit wants to expand. Right? This one exerts force this way, force this way, force this way, force this way, because of the magnetic field that gets created. This is a very weak force. A circuit you build on your desk is not going to grow. You can't see it. There's too much friction. But in principle, there's a sort of expanding force on circuits like that. Okay, let's go to the next example. Next little fun thing, which is magnetic braking. So here's the setup. It looks kind of similar. It's kind of a combination, at least this particular setup, and there are lots of different ways of magnetic braking, of making it happen. But this setup, I think, is the easiest to understand. So it's kind of a combination of those two. I'm going to take an object like this, a conductor, and I have a magnetic field that's created by some external magnet. Right? So this is not a magnetic field that's created by a current going through anything. It's a magnetic field that's created by something else. Like I have a sort of big north pole above the paper, a south pole below the paper from some permanent magnet. This is my magnetic field. And now what you notice about this, again, this is conducting and the rails are conducting. I have a circuit, but the circuit does not have any battery. Does not have any voltage supply. Instead it has a resistor, just for the sake of having one. If there wasn't one, we just take the resistance of the wire. And now what happens? So now, if you imagine that I give this conductor a kick, right? Much like so here it was moving through the magnetic field. We don't know what got it to move. Imagine we gave it a push and that's it. It's moving. Same thing here. I give this thing a push. It's kind of the setup from the Hall effect, except I put it on rails so that this closes the circuit. So what's the difference? Difference is that before, those pluses, they gathered up here, they had nowhere to go. The minuses gathered down here, they had nowhere to go. Now, this conductor moves through the field, so if you have a little minus, right, you get a force, and the force, you can work this out again. Right-hand rule is going to be down. If you have a little plus charge in here, you're going to experience a force up. Now, because current is defined in the positive charge direction, you're going to get a current that sort of goes counterclockwise through this wire. Now, we figured out before what the potential difference was, right? The potential difference between this and this is given by the length of it, times the speed, times the magnetic field strength. So we get a potential difference between this end here and this end here. Right, so delta V between, how you can draw this effectively. Pretty much used all my colors somehow. Used it in red, I guess. Delta V between the top part and the bottom part. So this moving bit here kind of functions as the, let's call it the battery of this circuit. We're going to come back to this example later in the context of induction, because you can sort of think of it as our first encounter of induction, where motion with magnetic field creates a current, but we can understand this example entirely in terms of magnetic forces acting on charges. So hopefully you can see that there's now a current where the positive charges are going up and around, or they try to, and the negative charges are going clockwise, because of the conductor moving through the magnetic field. So make sure you understand this before you move on. Okay, so what do we have? We have a piece of metal with a current. Oops, what did I do? Current going this way, right? And that thing is in a magnetic field. So I've got a current this way, magnetic field down, so there's a force to the left. Now if I look at the individual particles, plus charge moves up, field down, force to left, and negative charge moves down, field in, middle finger points right, but because it's negative, the thing gets flipped, force is to the left. So the force opposes the velocity. It's a braking force. This is a two-step process, right? So let's make sure you understand it. It's a two-step logic here. The first step is this piece of metal moves to the right, which means any charge inside the piece of metal is moving to the right through a magnetic field. That will make positive charges go up and negative charges go down. But because they're hooked up to these rails, they're conducting, these charges can start moving around and I get a current. The current is of course given by delta V that we worked out here, right? We write down what it is from before. It's the length. Let me call this separation L. I call it delta X above. It's L times V times B. So I'm going to get a current. I get a current I, and I is going to be delta V over R, so L, the length of the metal, at least the connecting part, right, the distance between the two rails, times V times B over R. Now this current is then going to cause a force on the piece of metal, right? This is now essentially this piece of metal, this piece of conductor is now a wire that's carrying current up inside a magnetic field. And so I can figure out what is the effect due to that. And it's going to be a force to the left. If the magnetic field had pointed the other way, right here, I pointed upwards out of the page, then the current would have been the other way, and you can double check that it still gives you a force that's to the left, opposing the velocity. Right, so again, two steps. Piece of metal moves through field, that creates the current. Now I've got a current in a field, that creates a force. And no matter how you orient your magnetic field, you're going to get a braking force. And that's good. Well, it's reassuring, because imagine there wasn't. And I could just give this a push, it moves through the magnetic field, and I get a power output through my resistor. Like, where is that energy coming from? It would be like magic, right? No, what we are getting is that the kinetic energy of this is converted to essentially electrical energy, right? So I give this a kick, and it moves, and it slows down, and the initial kinetic energy that it has is converted to the power output of this resistor, right? The energy output, total energy output of this resistor. Now, if you work through the math, and I suggest that you do that, and you start with some velocity, you can figure out that you can calculate, you can confirm that the total power output here, you know about the power output of resistors, is equal to the kinetic energy lost by that piece of metal. Now, because the velocity changes, like it slows down because of the braking force, that then means that the rate at which it slows down is going to get down. So the slower it is, the less the force, because it's proportional to V. It's a little bit like air drag, where the faster you go, the bigger the force that's braking you, and as you slow down, the force becomes weaker. Same thing here. The faster you go, the bigger the force, right? QVB. This thing here, QVB. So the bigger the current, the bigger the braking force, but as you slow down, the force becomes weaker. So you actually sort of you start slowing down fast, and then your rate of deceleration becomes less. And if you want to actually solve this mathematically, you have to solve a differential equation, and I'm happy to talk about that some other time, but right now it probably take me way too long to include this in this video. But it's a nice little thing to think about. Magnetic braking is used. For example, you can use it to, say, brake trains. The setup would be somewhat different, but one nice thing is you can make this work, that you get magnetic braking without actually having to make contact with something that like rubs against something else. So you can brake something without friction, which means it's not going to wear out, unlike the brakes in your car, say. And the textbook, I think, has a nice example of how you might get that kind of setup. So this is cool stuff. If you get a chance to look at some magnetic braking effects in the lab, so if this were a real classroom and not virtual, right, I'd actually show you some effects that you're like, whoa, this is crazy, right? You have like stuff falling, and it seems to be then sort of slowing down in its fall significantly. Now, of course, what you could do is you could instead apply some other force to keep it going, to oppose the braking force. Now, if you do that, you essentially get a basic generator. Here's the basic generator. Imagine I have the same setup as before, and now hooked up to a light bulb rather than a resistor, but that doesn't really matter. It's the same thing. Right, here's my magnetic field. And now imagine I move this piece of metal with some velocity v. It's going to experience a force, a braking force, right? The braking force is, well, the braking force on a wire is I, the current, times L, the length, times B, the field. And maybe I should have written this down at one point in the previous example. Let me go back to this very briefly. Right? The current is this, and then the force is equal to the current times the length times B. So we can put those pieces together, right? We plug this into here, and we're going to get L squared V B squared over R. Alright, fun stuff, right? Okay. So that's the strength of the braking force. So, if you then pull, right, the other way with a tension that's equal to the braking force, tension, you're going to keep a constant velocity. Of course, some poor sod, drawn here, has to be pulling this along. Now, maybe you get your donkey to do it, right? That would be fantastic. That would help a lot. It means you don't have to do it. Maybe you can roll this down a hill and let gravity do it, but then you have to move this chunk back up, right? So it's kind of a trade-off. You still have to put in the energy somehow. In this case, it's that person doing work and converting his metabolic energy that he got from eating a cereal at breakfast to ultimately the power output of the light bulb. But that's the idea of a generator. You convert essentially some other form of energy into electrical energy, electrical power output, by dragging a conductor through a magnetic field. Right? And if I keep pulling to oppose the braking force, I'm going to have a constant velocity through the field, therefore a constant power output here. Now, of course, eventually those rails will end, and then what? Maybe I can have some people, if you imagine this like up a hill, and maybe the thing just rolls down the hill, there's a bunch of people who keep bringing those things up the hill, right? That would work, I guess. But you could also just construct it this way. Imagine instead of having a bar on rails, I have a sort of bar here. This is my bar. And it's the middle of it attached to a thing that can spin. So this whole thing can sort of spin around like this. And then out here it's resting on some kind of, conducting rail that's hooked up to my wherever I want to use that electrical power. And now, if this thing keeps moving, and now you can just put your donkey in front, and the donkey goes in a big circle, like some kind of, like a mill or something. Right, you can use wind, right? Like a windmill. You have wind blow on it. The wind makes this thing spin continuously by the continuous force. And as it moves through the magnetic field, it's going to create a current. Like right now, object moves this way, field is down, so current would be this way. Of course, that will cause a braking force because current down, current towards the center, field into the page. Can I show you this to you? There we go. Force my middle finger here this way. But I'm going to oppose that force because the wind's blowing against this, and with beautifully shaped blades, it makes it spin, keeps it spinning. And so I'm going to get a continuous current. Now this, you can imagine, this gets hooked up via some kind of cable that goes like underneath this whole setup, and it goes around here. And I get a continuous power output as long as something keeps it spinning. So we've just built our first wind power station. Of course, it doesn't have to be wind that makes it spin. It could be that you hook this up to some kind of wheel where the water runs through. It came down a hill. You've got hydroelectric power right there. Maybe you pump hot steam at high pressure through some kind of turbine that spins fast as a result of the high pressure, and you've burned coal to make it happen for the coal power station. Maybe you've heated water using radioactive fission. Heated water to high pressure by essentially with a bunch of uranium. well, that high pressure might be enough to turn the wheel. Whatever force it is, it doesn't matter. Ultimately, as long as we've got some force that opposes the braking force, and this thing keeps spinning, it's going to keep producing power. So that is pretty much the principle, the basic idea, how every single power station works. Some sort of solar technology, that's a bit different, right? You can use solar energy to just heat up water and get high pressure steam, and that'll work the same way. Then you use high pressure steam to spin a wheel. But, I mean, you can also just use the sunlight directly converted to electrical power via certain processes. That is different. But pretty much anything else, any other power station works by making something spin. And the thing that spins, ultimately, is a piece of conductor inside a magnetic field. And the force provided by the water, the wind, the hot steam, whatever it is, it opposes the braking force and therefore keeps it spinning, and I want to keep getting a current created via that. We can treat those examples again in the context of induction. I will talk about magnetic flux, but we don't have to. We understand the principles just from understanding magnetic forces. Now, there are two more examples. One is the electric motor, and I didn't draw this out because I think the book does a better job. It'd be sort of hard for me to do. Let me show this to you. So here, oops, I'm running difficulty with my camera here. See if I can fix this. There we go. So this is the picture of the electric motor that's found in the book. Let me explain this to you. So the way you can electric motor, so an electric motor does what? It converts electricity, right? Meaning some kind of electrical power into motion. So how would you do that? Well, this just goes back to understanding the forces on wires. So what I imagine I do, I have a circuit, you can see it here, right? And it gets hooked up to this, I'm going to come to that in a second, this little metal thing here. But the current's going to run this way, to the wire, up here, and then here. Now, because you've got a magnetic field there from some permanent magnets, like a North Pole and a South Pole, you can work out what the direction of the forces are on these pieces of metal, namely this one here and this one here. And the overall effect is that that thing wants to spin. Right. Now, if you just do that, it would stop after like half a rotation. Or it would sort of oscillate like this, back and forth. It's a different calculation you can do. What's the rate of oscillation? Another fun problem. But so here comes then the ingenious thought. If once it's sort of spun like to here, so what it wants to do, right, it wants to go here, and then you can figure out what it wants to do would be this. But then what you do is that you flip the way the two wires are connected. And the way you do this is you have these wires here, and they brush against a thing called a commutator. And as soon as what this wire setup has turned enough, the direction that the current goes through this piece of wire flips because it's connected the other way around. You can sort of see this if you look carefully at this diagram. Then the current goes the other way around suddenly. That means the place it was now is again wrong, so it keeps turning. It wants to go here. Okay, now it's flipped again. That again reverses the current, so again it's kind of in the wrong position. There's again a force on it, it wants to keep going. So it keeps spinning, 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 spinning. That is a basic electric motor. Now the real electric motor might have more than just two connectors to make the whole thing smoother. It might be split like 4 or 6 or 12 or something, with alternating plus, minus, plus, minus. But that's beside the point. The basic principle is this. The basic principle is this, with this reversing direction of the current using this commutator method. And that's something you can build. A little kits you can actually get, if you have the time of the summer, why not just get one of those build your own electric motor kits. You can get them fairly cheaply online, and you can put it all together yourself. And you connect it to a battery, you give it maybe a little push to get it started, it'll spin, 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 spin. Okay, that was another example. It would be another good thing to make sure you understand. Now then, the last thing I wanted to show you, and again I'm going to use the book for this, I'm going to show you what I wrote down, is the concept of eddy currents, and they're closely related to magnetic braking. I'm going to show this to you too. So here's a good picture in the textbook on eddy currents. So this is in chapter 30, at least if you're in the my 162 course. If you're watching this from a 115 course, then it would be, I don't know, chapter 25? I think it has the same diagram in it. But here's the idea. We are moving, so imagine what you've got is you've got two magnets, a north and a south pole. Or maybe it's one magnet that's connected, doesn't matter, I don't care. The north pole here, south pole here. So I've got a magnetic field that points straight down. Right, from north to south. Now I'm moving a metal sheet through this magnet, through those two magnets. It's kind of like shown here. So I move it, velocity is to the right. And you pull it, right? So you can figure out that because it's made of conductors, right? It's a conductor, so it's made of little charges that are free to move. Those charges will want to move to the back of the sheet, as it's drawn here. So velocity this way, field down. Why do I always have to break my wrist to do this? Velocity, okay, I can't do it. You do it yourself, right? Velocity to the right, field from north to south. So the force is going to be into the page, like to the back. So you get these currents that are like this. The little charges here get pushed to the back. Now, they would gather there, but they don't have to because there's space to the left and right. So, because all those pluses here don't like each other, the minuses here don't like each other, it's like the Hall effect. Now they're going to spread out sideways, because there's no magnetic field over here, because the magnet's only like in the middle. So you get these currents that go like this. These are called eddy currents. Eddy currents are currents, there's closed circuits, but they're not happening in some kind of wire setup, they're happening in a solid sheet of metal. Now they're hard to actually track, hard to calculate, but I hope the basic idea is clear, right? There's a magnetic force in the middle, this way, that moves charges. They don't want to gather because they don't like each other because of electrostatics. So they move to the sides, and they get pushed around, and they keep going in these loops. But one effect of that is that then I've got a current in the middle that goes towards the back, from the front of the sheet to the back of the sheet. Now, you use your rules, and you're going to get a force to the left, right? So, current into the page, hard to show you. Field from north to south, you can do this. I'm going to break my wrist here. The force, you can double check, is a braking force backwards. So I get an eddy current, at the same time I get magnetic braking. And that's close to the kind of principle you might use, say, if you want to brake a train. So here's the picture for that, in the magnetic braking system, where I have magnets, and they might be like electromagnets, and they move. Like this would be the rail, right, on which the train is running, and those are not touching. So left and right of the rail, and it moves this way, and then I turn those into magnets. I'm going to get eddy currents in the rail, and the eddy currents then want to push the rail forward, and so similarly the train gets pushed backwards by Newton's third law. It experiences a braking force. It's a little bit harder to see how the directions are on this example. This one is easier to understand, I think, but the principle here is the same. And here you can say, okay, this is going to brake without wearing out anything. Nothing, there's no friction between any two parts here. All it'll do ultimately is warm up the rails a little bit. But that's okay. Okay, so here we go. I hope those were some fun examples. Electricity, magnetism, they really come together. They interact with each other, and there are lots of cool effects here. This was only the beginning. We're going to talk more about induction. But make sure you understand everything I talked about in this video, right? There was no new material per se, no new physics. It was just applications of understanding magnetic forces, how they act on moving particles. Alright. Maybe watch it again if you're still confused by some of those things. It takes time, right? It takes time to not break your wrist all the time. But I think you can do it. Also, if you do break your wrist before the exam, please let me know, because you're going to get accommodation.